Hello everyone. Okay, let me start. My name is Utkarsh Gupta. I am currently an instructor and manager at Scalar. Before working in Scalar, I was in Google Munich, Germany as a software engineer. I was working in the sign up flow of Google. So when we sign up in Google, how the flow looks like, I was working there. And before that, I was in my college. In my college was JP Institute, Noida. I used to do a lot of competitive programming, like Code Forces. I was master in Code Forces, then 6 stars on Code Chef, and I have basically participated in a lot of competitions, like Google Hash Code. I was first ranked in India in Google Hash Code 2019. That was the first time when Google Hash Code happened for global, like for all the countries. And I did a lot of internships in my school days, like college days, like Microsoft, Geeks for Geeks, HackerRank. This was a brief introduction about me. Now, setting an agenda for today, we will be discussing binary trees from very basics, and we will discuss what is a binary tree, how to maybe travel the binary tree. We'll solve some good questions on binary tree as well, and then we'll discuss what is a binary search tree. That is a specific version of binary tree, which is very important. Like what is the binary search tree? How do we make it? And we will also solve in the end one question that I solved in a Microsoft interview when I applied for intern. Luckily, I was able to solve there, so I cleared the interview. I got the internship. So we'll discuss that in the end. All right. So is the agenda clear for today? Prerequisites are nothing as such. So just in case, if even if you just know what is a linear data structure, like maybe an array or a linked list, that is enough. Like if you know what is a linked list, that is enough to start. We will discuss about hierarchical data structures from the basics. Sounds good to all? Looks good. We will not be using any specific language. We'll try to cover in pseudocode way. We'll try to do dry runs so that even if you guys are comfortable with any programming language, you can code it. So as long as we know what to code, coding becomes easy. If we exactly know what to write in the code. Syntax is just like depending on programming language, whichever you want. C++, Java, Python, anything. So we'll try to, do the dry runs more. All right. Now guys tell me, if someone asks you, where is the root of the tree? What will be the answer? Where is the root of the tree? Some of you are absolutely right. Some of you are incorrect. Guys, if we draw a tree like we used to do in our school days, how is tree looking like? This isn't this our root? No. So it's bottom, underground, not top. Does it make sense? Now this in computer science become a inverse. So being a computer student or being a tech person, if we know about binary trees, we know this root always lies at the top. But actually in the computer science, this tree is treated like this. So you will find root at the top and leaves at the bottom. Now let's see how is the structure looking like. So first of all, binary tree is a hierarchical data structure. Guys, do we all aware of the term hierarchy? Do you all know what is the meaning of hierarchy? Yes, right? Hierarchy. So if we have maybe, let's suppose if you're talking about a company also, in your company also, you'll see we have a CEO, then we have some vice presidents. So CEO, then vice presidents, then we have some team leads, then we have some engineers, software engineers, and so on. So this is a hierarchy which we have. Similarly, we can see hierarchy in anything, right? Yes, principal, teacher, student in the school also. Yes. So all the hierarchy. So we are aware of the term hierarchy, right? Also, if someone asks, what is the meaning of data structure? Can you guys tell in one line what is the data structure? Like what is the meaning of the term data structure? Organized way of storing and managing data. Does this make sense to all? Data structure in general means an organized way to store and manage data. So we can do it using an array. We can do it using a stack. We can do it using a linked list. We can do it using a queue, map, set, anything. Does it make sense? Yes, no, so far, right? So all of this are data structures. So binary tree is also one of the data structures, which is like this particular tree that we see. So let me draw it for everyone and then we'll see how this looks like. So let's say we have this particular as a node. Before this, guys, are we aware of linked list? Like how many of you are comfortable with linked list? Yes, no? Majority of you are comfortable. Some people are not comfortable with it. Okay. Let me just give a quick idea about what is a linked list. So you might see that in an array, when we store something, it is a continuous memory allocation. So maybe if you have element 7, 3, 5, 6, 2, 1, something like this, if this is our RAM, then if 7, this particular 7 is present in this particular block, then this particular 3 will be present in this particular block. It is continuous in memory. Does this make sense to all? So array, if we talk about linked list basically says it is not continuous in memory allocation. Now, when we say about linked list, we can have one node if this is our RAM. And let's suppose if one element is present over here. Let's suppose if you want to store maybe element number 7, then you want to store element number 3, then you want to store element number 5. In an array, it is very easy because in an array, what we do is we store in a continuous memory allocation. So if we have to maybe find any element, it becomes an easy task. What if we have this as an array A? We'll just do A of 2 and we'll get this particular element 5. Yes, no. Are we all comfortable with arrays? Like, please click yes if we are all comfortable with arrays. Nice. Nice. So array is basically very simple. Like you can access anything very easily. In case of linked list, it becomes a little tricky because if let's suppose 7 is present over here, let's suppose 3 is present over here, and let's suppose 5 is present somewhere over here, then how will we know that where is our element? So if you want to maybe find the second element of a linked list, how we will get there? So linked list basically says always keep track of the head node, that is the first node, and from the head node make a pointer pointing to the next node. Here's the head node. From the head node we have a pointer. This pointer basically points to 3, this pointer points to 5. So if we are currently standing at this particular element, we will know, okay, for the next element we can reach this particular memory, and for the next element we can reach this particular memory. This way we are able to reach all the elements in the linked list. And the last element's next pointer points to null. So basically every element we can access in a linear traversal from left to right. That is starting from the head node, we can reach all the node of a linked list. Does that make sense to all? It is not continuous in memory allocation. Hence, we need this next pointer. Are you all comfortable with linked list now? Yes, no. Linked list is basically a non-continuous memory allocation where we start from one particular node as a head node, and then using the next pointer, we can move to the next nodes. This same strategy is also used in a binary tree. Okay. The same strategy is used in a binary tree. Now, binary tree structure says instead of just having a next pointer, let me draw it like this. We have this particular node. We have some data like this 735. This is our data. And we have two pointers. Instead of one next pointer, we'll have two pointers. One is basically known as a left pointer. One is known as a right pointer. Left pointer will point to the data present at the left node or the memory allocation there. And the right pointer will point to the data of the right node. Correct? Make sense? Yes, similar to double linked list, correct. Now guys, if we have to define any you can say data structure or any maybe data type that follows this, maybe using a structure or a class, can we do this? Can you guys just take one moment and try to think how you will define a class for this particular node? So if we say this is a node, this entire thing is a node, and we have to define a class for it. How we will define a class for it, guys? Yes, some of you are right. Nice. So we'll just say class node. And since we need a data can be anything. For us, let's say we have an integer data. We can also make it a string data, character data, any data that we want. There is no restriction whatsoever. Is it clear? Like data can be anything, not just integer, double, float, anything. You want character, you want string, you want a list, that's also allowed. And we need pointers to the left and right pointer. So we'll have node, left, right. These will point to the nodes of left and right side. This is it. Is this class clear at all? So we have a data, we have a left pointer, we have a right pointer. That's it. Simple. So is this making sense? Like if we have a node, this is how we define a node, right? So if we basically try to define a tree, let's take an example of a tree. So maybe let me draw one particular tree. Let's take very basic data, that is 1, 2, 3, 4, 5, 6, 7, something like this. Let's suppose we have. Okay, this is 8. Now what we are trying to say is similar to the linked list where we have a head node to start with. In a binary tree, we have a root node to start with. This is our root node. As we mentioned in the computer science, the tree is actually an inverted tree. This is our inverted tree, where root is at the top and leaves are at the bottom. Correct? We will define what are leaves in some time. Please try to refresh. In case you are facing any issue, please refresh once. All right. Can we have number 2 or 3 or vice versa? Yes, these are any random data. There is no specification. You can have 1, 2, 3, X, Y, Z, 10, 20, 30. Your names also totally fine. No problem with that. Now, guys, similar to linked list, where we have the last node pointing to null, for the nodes here, we will have the left or the right pointer, which are not pointing to the current node, they will point to the null node, which indicates there is no data there. Make sense? So we'll have this pointing to a null node, this pointing to a null node, because for every node, we are defining a left and right pointer. So left and right for everything will point to null. This will point to a null node, and this will point to a null node. So far, so good? Yes. Now let's define some terms in this. There are some terms that we should take care of. Number first is leaf node. So what are leaf nodes? Any node which does not have a left or the right pointer, or both the pointers pointing to null. So node where left and right points to null. How many leaf nodes do we have? Correct. We have 1, 2, 3, 4 leaf nodes. What are the leaf nodes? 4 is one of our leaf nodes, 7 is one of our leaf node, 8 is one of our leaf node, and 6 is one of our leaf nodes. Because all these elements do not have a left or the right side. So this makes it like an inverted tree. Like we have root over here and we have leaves at the bottom. So far so good to all. And if we look actually in the memory, they are randomly placed. Like 1 is placed at a different memory location, 2 is placed at a different memory location, 5 is placed randomly anywhere. Now, the advantage of linked list and trees over arrays that you don't need a big piece of chunk in a memory, like continuous piece of part in a memory at a point. Even if you have distributed free available spaces in the memory, linked list or trees make best use of it. Is it clear to all? Like if you are maybe creating an array, the array needs a continuous part of memory, which has to be big if you want big data to store, like a lot of data to store, which is not available all the times because memory is limited. You cannot have an infinite memory, right? But a linked list or a tree, linked list or a binary tree, make full use of memory that it uses every place which is free. Like try to use all the allocated places which are free. All it needs is one continuous part which can store the data. So for example, if we have a integer data type, it needs to store the 4 byte data at a point and the point of left or the right pointers. That's it. So is it clear that memory management is good in linked list and binary trees over arrays? Yes, no. Now this hierarchical data structure is also used in some kind of databases. So can anyone name any databases in real life where we use this? In MongoDB we use it. In SQL, if you'll notice, there's a B tree kind of structure which helps in indexing in database. So if you have studied database management system, like if you know like MySQL database also, we have a B tree, which is also a hierarchical data structure that can help us access any element in a database very fast. So are the real life use cases clear to all? Like we have good databases that also use hierarchical data structures so that they can access anything very fast. Some NoSQL databases also use it, some SQL databases also use it, and a lot of places that is used. Now, is binary tree only tree available or can we have multiple trees? Like we can have different kind of trees, we can have different structure of trees depending on how many children we can allow from a node. Now, what is the children? So, guys, if we look at any particular two nodes which are attached to each other, so maybe let's pick up these two nodes, or let's pick up these two nodes, or let's pick up the entire subtree for simplicity. These three nodes, let's say, if we are selecting this particular structure, this particular entire structure is a parent-child relationship in computer science. So we call it like a parent-child relationship. So 5 is parent of 7 and 8. These are just the namings, how we name them. 7 is left child of 5 and 8 is right child of 5. Are the namings clear to all? Like what is the left child, what is the right child? So if I ask you what is the left child of 2, what is the answer, guys? What is the left child of 2? Yes, 4 is the left child of 2. So from 2, left child is 4. Similarly, if I ask what is the left child of 3, what is the answer? Null. Very good. We don't have a left child of 3. Its left child is pointing to null. So are the terms parent child clear? Like parent child relationship? What is the parent and what is the child? Yes. Nice. Now using the same nomenclature, if we want to relate 2 and 7, what will be the relationship between 2 and 7? Using the same nomenclature. So if 5 is a parent of 7, 2 is a parent of 5, then what is 2 with respect to 7? Correct, grandparent. So 2 is grandparent of 7 and 8. So it's like a family tree. Like we have like children, then parent, then grandparent, great grandparent, and so on. It's like a hierarchy. Making sense? Similarly, if we want to look at the entire chain, we say ancestors. So if someone wants to ask what are the ancestors of 7? Ancestors of 7. What is going to be the answer? Correct. 5, 2, 1. So parent, grandparent, great grandparent are all the ancestors of 7. Make sense? Similarly, based on this only, this naming of a family tree, if we want to have a relationship between 7 and 8, what is the relationship between 7 and 8, guys? Correct. Siblings. If I want to know what is 6 with respect to 5, so if you have a parent, your parents, brother or sisters, son or daughter, what is that? Correct, cousin. It's like a family tree. Right? So are these namings clear to all? Just remember your family tree and you'll get all the namings. So parent, child, grandparent, grandparent, ancestors, siblings, cousins, everything. Like it's like a family tree. Right? And we have a root at the top, leaves at the bottom. Yes. This follows only 2 kids, not more than that, because it's a binary tree. So as long as we are talking about binary tree, this name itself says at max 2 children. So instead of this, if we would have a ternary tree, then we can have 3 children. If we would have a k-ary tree, we can have k children. But right now we are talking about binary tree, so at max 2 children. Making sense? Only 2 kids. Don't have more than that. What is cousin? Cousin is basically your parents' brothers or sisters' child. So in the same level, a different child. That is a cousin. Simple. Right? So far so good. Just remember your family tree, remember your like ancestors, and you'll get to know okay, what are this with respect to this and so on. Okay. Now there is one more term. So when we have left and the right child, we also have a term left and the right subtree. So like guys, do we remember what is a subarray? You know what is a subarray? No, subarray. So when we say about a array, look, this is a sub this is our array, let's say. Then a small continuous part of that is known as subarray. So if I pick this particular part up, this I can say is one of our subarray. Okay. So basically a continuous part of an array is known as subarray. Is the term subarray clear to all? So in the continuous array, just pick a small part. That is a subarray. Similar term here, that is a subtree. Yes. In the array, sub-array has to be continuous. So you cannot just pick 7 and 5. You have to pick 7, 3, 5. Similarly, in this, we have a term subtree. Now, subtree is defined as, with respect to one particular node, all the, you can say, children, great-grandchildren, everything below that is part of that subtree. So, for example, if I talk about this blue circle, this is a subtree of 5. Let me write over here. Subtree of 5. Make sense? Even node, yes, entire subtree, like node 1 subtree is the entire tree. So, if in general, if I have to ask this is a subtree of what, guys? Like 3, 6. This is a subtree of, correct, subtree of 3. The highest node will define what is the subtree of. So, for example, this is a entire family of this 3. So, this 3 has only one child. Similarly, this is the entire family of 5. So, all the entire family of one particular node, which is at the topmost node, the entire family of that node is a subtree with respect to that particular node. Right? Now, this is also a right subtree of tree. So, right subtree. This is also known as a right subtree of 1. So, of the root node, it is also acting as a right subtree. Similarly, if we want to know what is the left subtree of 1, the entire subtree of 2 is the left subtree with respect to 1. Are the term left and right subtree is clear to all? Yes, 7 and 8 together cannot be a subtree. So if we want 7 and 8, we have to include 5. Then it becomes a subtree. So is the term subtree clear to all and the left and the right subtree are clear? Yes, no? So this is some common terms about trees anyways. 2, 4, 7, 8, 2, 4, 7, 8, 5. That is a subtree. So this is the entire subtree of 2. And it's also a left subtree with respect to the root node. Make sense? Yes, no? Can leaf node be a subtree itself? Yes. Very good question, Shubham. So, guys, if I ask, if I'm just taking one node, let's say if I'm just taking 6, can I say that this 6 in itself is a subtree? Yes or no? Yes. Guys, the answer is yes. This is a subtree of 6. So, subtree considered like a family. So, maybe this is a bachelor. Does not have married, no kids, living alone, enjoying the life. So it is also a subtree. So even a single node, which is a leaf node, can be considered a subtree. Correct? So the entire family of one particular node is a subtree. Nice. Similar to any single element in the array. Null pointers are not part of subtree. Null pointers is just a different thing. Yes. Okay, let's do a few more terms. Guys, when we say about height or let's suppose depth, in general, what comes to our mind when we say about depth? How deep something is? Yes. So let's suppose if we are talking about a container, something like this, a container is there. How deep is the container? Yes. When you talk about depth, from a given particular point, how deep it is, that is a depth. So if you are having maybe a bucket full of water, how deep is the bucket? So this depth in terms of this tree is basically the distance from the root node to the current node. So distance from root node to current node. That is the depth of the tree. So if I want to ask, okay, what is the distance? Let me also define this term distance. Distance is basically number of edges. Now what is the edge? These arrows basically are known as edges. And these things are known as nodes. So the squares that we have drawn that stores the data are nodes. The arrows, basically the left and the right pointers, are our edges. So the number of edges that we travel from the root node to the current node is the depth. So if I want to know what is the depth of, let's say, 5, what is going to be the answer, guys? What is the depth of 5? Like how many edges do we travel from the root node to the current node? Correct, 2. We travel 2 edges. That is, from 1 we'll reach 2, from 2 we can reach 5. That are 2 edges that we travel from the root node to the current node 5. Is the term depth clear to all? Okay, let's do one more term, height. Guys, when a height comes in, then can we say with respect to something we see a high, how high is something with respect to a base? So for example, if we want to talk about a height of a mountain, guys, with respect to what we calculate a height of a mountain, do we know? In real world, if we talk about height of a mountain, yes, with respect to sea level. Because sea level is same throughout the world. Like that is a base with respect to which we calculate how high is something. Similarly, if we maybe see some famous statues, then we also talk about how high is the statue from the ground level, right? Then ground is a base. Hence, in this case, when we talk about height in the tree, it is the distance from of or from current node to farthest leaf. So distance again here is same as number of edges of the current node from the farthest leaf. So if we want to talk about, let's suppose, height of maybe 3, what is the distance of 3 to the farthest leaf, guys? 1. Very good. 1. 3 is basically having one child 6, and 6 is a leaf node. That is the only leaf node available in the subtree of 3. So the answer is 1. Now if I talk about what is the height of root node in this case, or let's say 1 in this case. What is the height of 1, guys? The distance between the current node and the farthest leaf. Yes, 3 is the answer. Very good. Guys, 3 is the answer because the farthest leaves will be 7 and 8. When we say about farthest leaf, the farthest leaves are 7 and 8. So we will not consider 6 or 4. So we'll go from 1 to 2, from 2 to 5, from 5 to 7, or 5 to 8. 3 edges we are traveling to reach the farthest leaf. So the height is 3. Is this clear to all? Yes, no? Now there is a term height of a tree. So if someone says what is the height of a tree, the height of root node is also known as height of a tree. Correct? Let me also write it down. Height of root is equals to height of tree. So if I ask what is the height of this particular tree, what is the answer, guys? Correct, 3. Because height of 1 is 3. So the height of root is equal to height of tree for this example is 3. Make sense to all? Yes, no? So far everything making sense? So far now are we comfortable with this data structure? Like what it looks like? What are all the nomenclatures? Let's move to the next part of the session, that is the traversals part 2. Traversal in a binary tree. Guys, do we know how do we travel a binary tree? So let me draw a tree for everyone. 1 and 7. Rest everything is pointing to null. Okay, rest everything is pointing to null. This is a tree, small sweet little tree. This is our root node. Guys, what are leaf nodes in this? What are leaf nodes in this? Correct, 4, 7, 6. Very good. These are 3 leaf nodes. Nice. Now there are 3 ways to travel the tree based on how we are selecting left, current node, or right. So let me explain this. Please pay attention, it is important. So we have 3 parameters. Parameter number 1 is left, then we have node, and then we have right. What does this mean? This means that if we are standing at any particular node, let's suppose if we are standing at the root node, what is the thing that you want to give priority first? So if you are giving priority to the left subtree first, then left will be selected. If you are giving the priority to the right subtree first, then right is selected. If you are giving the priority to the root node itself first, then it is selected. So depending on what is the thing that we are giving priority to, the traversals are decided. Our general practice is, in our general practice, we give priority to left before priority to right. So left is given a first priority compared to right. It is in a general practice. In practical, you can do opposite also. So you can also have right first and then so on. So we have three traversals based on this. We have an in-order traversal. In-order traversal says, let's give priority to left first, then the current node, then the right subtree. We have pre-order traversal. Pre-order traversal says, let's give priority to the current node first, then left, then right. And we have a post-order traversal. Post-order traversal says, let's give priority to left first, then right, then the node, current node. So basically, if you have to perform any operation, depending on the priority, we will perform those operations. Make sense? So hypothetically, let's suppose if the operation that we want to perform is, let's say, just printing the element. So just printing is our operation. So our operation is print node. We can do any operation that whatever we want. Maybe if we want to update anything, delete anything, do anything we can do. Do some mathematical calculation, that also we can do. For simplicity, let's suppose our operation is printing the thing, just printing. Okay. So let's see how the in-order traversal will work. All right. Right now we are standing at a root node. We always start anything in a root node. So whenever we have a binary tree in front of us, always start from root node. Is that clear to all? Like always start from root node if you have a binary tree in front of you. Nice, nice. Any time, in any situations. All right. Now, in-order traversal says, I will first give priority to the left side, not the current side, left side. So let's move left. Again, the same thing is applicable. The 2 says, I will again give priority to my left side, then I'll come back to my current side. So again, we will move left. Now 4 will say, I will give priority to the left side, but I don't have any left side. So now I can give priority to myself. Is it making sense? The 4 is not having any left side, so 4 is giving priority to itself. So 4 is saying, let me give myself priority and let me perform the operation, that is printing 4. Clear to all? Nice. Now we come back to 2. 2 says, my left side is complete, so now I can give priority to myself. Making sense? Now 2 is printed. Now 2 will say, okay, my left side is complete, my current element is complete, so let me go right. So 2 will go right now. So now we'll go to the right child of 2. That is 5. Is it making sense? So we started from 1, then we went to 2, then we went to 4. 4 does not have a left child, we printed 4. We move back to 2. 2's left child is done, so we printed 2, then we moved right. Now for 5, again the same thing. 5 will try to give priority to the left side first, so we'll move to the left side. 7 will say, I don't have a left side, so I can give myself a priority, so I'll print myself. Now we will move back to 5. 5 will say, okay, my left side is done, so I can give priority to myself, so 5 will print. Now the entire left subtree of 2 is complete. The entire left subtree of 2 is complete. Can we say this? So can we say now 1 can give priority to itself? 1 will say, okay, my entire left subtree is done, I'm happy, so let me give myself a priority. Yes, so I'll give 1 a priority. Now 1 will say, let's move right, so we'll move to 3. Now for 3, we don't have a left child, so 3 can give priority to itself, so we will get 3 a priority, so 3 will be printed. And in the end, we'll move to the right side of 3, that is 6. 6 does not have a left child, so we can give priority to 6 and 6 will be printed. So this is how an in-order traversal looks like for this particular tree. Is the in-order traversal clear to all? Yes. Now take 2 minutes, try to write the pre-order traversal. If we have to see pre-order traversal, how the pre-order traversal looks like. We start from the root node 1. We will say 1 is giving priority to itself first. So we are giving priority to the current node first. Alright? So 1 will print it. Right? Now one will say, okay, I have given myself priority, let me move left now. So 1 will move to left. Now when we are standing at 2, 2 can give priority to itself. So we'll print 2. Now 2 will say, okay, myself is I'm complete, so let me give priority to the left child first. Left child is printed. Now 4 does not have a left or the right child. Right? 4 does not have a left or the right child. So we are done. The left side of 2 is complete. We'll move to the right child of 2. That is 5. 5 will say, let's print itself. Then we'll move to the left child of 5. It will print itself. Then the entire subtree is complete. The entire left subtree of 1 is complete. So we can move to the right subtree of 1. That is 3. We'll print 3. And we'll move to this and we'll print 6. Is a pre-order traversal clear to all? Yes. Now guys, what is the post-order traversal for this question? What is this tree? What is the post-order traversal? Come on everyone, please try at the post-order traversal. First go left, then go right, then give itself a priority. Nice, nice. Majority of right. Let's see. So we're starting with the root node. We move to the left child. From 2, we'll move to the left child. For 4, we will see the left child. It is not there. Right child, it is not there. So we can print 4. Now for 4, it is complete. The subtree is complete. So for 2, left side is done. So we'll move to the right side of 2. 5. For 5, we'll move to the left side of 5. That is 5. 7. 7 does not have a left or right child. We'll print 7. Right child of 5 is not present. So we'll print 5. Then for 2, the left and the right child both are complete. So we can print 2. Now the left subtree of 1 is done. This is complete. So we'll move to the right subtree of 1. 3. We'll print 3. Sorry. We'll move to the left child of 3. Right child of 3 does not exist. We'll move to the right child of 3. Right child of 3 is 6. For 6, left and right child does not exist. So we can print 6. Now for 3, left is not there. Right is done. So we can print 3. And in the end, we can print 1. Is the post-order traversal clear to all? Post-order traversal is go left, go right, then come to the current element. Making sense to all? Yes, no? Yes, nice. So this is kind of a pre-order, in-order, post-order traversals of the binary tree. This is how we travel the binary tree. Now guys, if someone asks to write the code of the traversals, can we try to write the code of maybe in-order traversal? So let's suppose if you have to write in-order traversal. Maybe if we have to just print it. So the operation is just to print. So void in order, and we are given a root node. So guys, how we will print it? Yes, you can write recursive code also, no problem. Let's first see the recursive version, then maybe we'll see the iterative version as well. So in the recursive version, if you have to write in order traversal, how we'll write in order traversal, guys? But they are same, like efficiency and everything is same. Yes, Surbi, thank you. It depends on what order you want to process. Nice. So guys, take 1 minute, have a thought on how we will write the recursive code of in-order traversal. Pseudocode is also good. So if you want to write pseudocode, totally fine, no problem. Just same thing. So in order, left, current, right. Pre-order, pre means before. So current, left, right. Post-order means post means end. So left, right, end. That's it. Depending on how you want it, so just depending on that, you can use it. Nice, majority of you are right. So let's write the code of in-order traversal. Guys, one tip to all, one important general tip. Whenever you see any question of a binary tree, first condition or the first statement in the code should be to check what will happen if my current node is null. What if my tree is not there? What if the root node itself is null? Does it make sense? This is a corner case of any tree question, any tree question. So please make sure that even if you are appearing for any interview or you are giving any written test, then you cover this corner case. What if the entire tree is empty? Okay, so if root itself is null, then what to do? We'll just return. We don't have to do anything because we have to print something which is there, right? So we just return an empty thing. Otherwise, inorder traversal says we will give priority to the left sides first. So let's move to the left side. So in order root dot left, we are moving to the left subtree. Now, if we consider that this function is actually printing the inorder traversal, can we say this function, this particular line will print the entire left subtree for us? If we believe that this function is printing the inorder traversal, then this particular line will print the entire left subtree for us, right? Then we can print the current road. And once the current road is printed, we can print the right subtree. So in order that's it. Sweet, simple 2-3 lines of code. So let's see and understand how this works. This is a random, like you can say pseudocode, not any specific language. All right, let's see how this works, shall we? Right, so initially we are standing at a root node. Root initially is pointing to 1. Let me use different color. All right. Now it is not equal to null. So what we'll say, let's move to the left side. So now the function call is, so from the function call in order 1, we made a function call in order 2. This function call we made. There are some statements which we have not yet executed, print and in order of the right subtree. From the in order true, we will make another function call because it is not null for in order 4. Right? Base case is this condition. Guys, how many of us are comfortable with recursion? Just yes, no? How many of us are comfortable with recursion? Nice. Majority of us are comfortable. That is nice. For those who are not comfortable, please don't worry. We will also do a iterative version of it. Sound fair to all? So in case you are not comfortable with recursive version, please don't worry. We will also do a iterative version. Will that be helpful for everyone? Nice. So let's do that. Let's do both. So right now, we are doing recursive. We'll also do iterative after this. So after this, from the 4 again, we have 2 more statements to execute. We are not executing for 2. Print and this. Now from 4, we'll make a function call to in order of null node because the left child is null. So we'll do in order null. Right? Now, once this is called, it will directly return because for null node, our base condition says just return, don't have to do anything. So we'll return it. This is complete. So it will now call the print statement. Printing of 4. So we'll print 4. So we'll have 4 as print, first print. Is it clear how we are getting 4 as our first print statement? Now we have printed. Now we'll call the third part. That is in order the right child of 4. Right child of 4 is what? Null. So we don't have null, so it will also return. So this entire function is complete. Can we say this entire function is complete and it will directly return back? Yes. This function completes. Thanks, Ronak. So after this, we'll have a print statement. Print of 2. We'll print 2 as the next element. After this, we'll have the right child calling. So in order, right child of 2 is what? 5. This function is called. So this is also complete. Now in order of 5 is called. It is not null. So we'll again do the calling of the left child. What is the left child of 5? Left child of 5 is 7. So in order of 7 will be called. Again, we'll have some print and other statements to execute. We are not executing that. First, we'll complete 7. So in order of 7 we'll call what? In order of null. In order of null will directly return. We don't have anything to do. It will print 7. We'll print 7 as the next element. Then it will again call the right child of this, that is in order of null. So it will again back return. So this all completes. So now can we say this is also complete? Now we'll print 5. So next element printed is 5. Now we'll call the right child of 5. Right child of 5 is in order null. That will also return because directly it's a base condition, we are returning it. So now in order of 5 is also complete. Now what we'll call the next statement, guys? Guys, what is the next function call we will make? Correct. Printing 1. Because the in order of 2 is complete. We have completely successfully called the left subtree, successfully called the current node, successfully called the right subtree. Now we'll print 1. So 1 is printed. Now we'll call the right subtree. Right subtree is what? In order of 3. Now from in order of 3, we will say we'll call first in order of null node. That will return. So in order of null node, we will return from there. Then we'll print the 3. Then we'll call the in order of 6. And we'll print 6 because left and right subtree is null. So is it clear how this is working? Like how we are able to print it? Yes, no, yes, no. Yes, we'll do iterative, don't worry. Guys, before we do iterative version of this, let me ask you this. If I have to write the recursive code of pre-order traversal, what are the changes in the code that we need? How do we write pre-order traversal? Correct. Instead of first making a recursive call, then printing, if we just swap this, that is first we print, then we go left, then we go right. So this is left, this is node, and this is right. So if we just swap node and left, we will get a pre-order traversal. Yes. First print, then go left, then go right. Similarly, if someone wants to maybe use the post-order traversal, then first go left, then go right, then print in the end. So these two swaps. Swap, post-order. Is this clear to all? How do we get pre-order, post-order in order? Nice. Now let's do the iterative version. So if someone says to do it iteratively, can you guys please take 2 minutes, maybe use pen, paper, or another tab in the same computer or laptop and try to write a code there of in order iterative traversal. Don't write the code in the chats. It may be a little long, like few lines, but maybe use pen, paper, or another tab to write the code. Once you are done writing the code, can we get just type the word done in the chats, like DONE in the chats. That's it. Good, good, nice, nice. Guys, recursion internally works like a stack, recursive stack. Have you heard of the term recursive stack? Recursive stack. Oh, yes. Recursion internally acts like a call stack, recursive stack. So maybe after the call, please try to see about recursion a little bit. Like in the recursion, when we do a function call, the remaining calls which are not yet executed, like in this case, when we were calling the left subtree, the print and the right subtree is not executed. That is a part which is stored in a stack which is not executed yet. So once the left subtree is complete, the function comes back and the current node and the right subtree is printed. It's like a, you can say, last in first out structure. Guys, do we all know what is a stack? Like last in first out structure. Like stack of maybe plates. When we go to a marriage, we see some plates. When we go to eat food, we just pick up the top plate. In case someone wants to put more plates, that person puts more plates. Similarly, in case of our school days, if you remember, when we used to get our notebooks checked, we used to go to the teacher's desk and maybe place a notebook. Then other person will place a notebook above that. The other person will place a notebook above that, and teacher will pick the top notebook and check it first. So notebooks are coming on the top and going first. That is a stack. Do we all remember stacks now? Like stacks. So if we have, let's say, 5 books in front of us, we can place a book only at the top and pick up the book only from the top. Yes, bangles in the hand. Yes. So in the hand, if you wear bangle, like you can put the bangle only at the top. Like if your hand is like this, the next thing coming up will be on the top. And when we have to remove it, it will the only top element you can remove. You cannot just remove middle element. Like if you have to remove the middle bangle, you have to cut your hand. You don't want to cut your hand, right? So remove the top bangle, and then one by one you can remove everything. That is a stack. So stack is a best replacement for recursion, in which we place it and this. So it's a last in first out, LIFO. Last in first out data structure. Make sense, Tom? Now question is, how is this useful? Like how can we use it? Like how is this very important for us? So let's take this particular tree. Let me just I'll see this. Like this is a cool, right? Just using the above tree. Okay. Now, guys, when let's suppose if we just consider an in-order traversal, right? When we were standing at this particular node number first, then we know that in-order traversal says left, then current node, then the right child. So we don't have a choice but to go to 2. Can we say we don't have a choice, but we have to definitely go to 2 at all the point of time? Like there is no particular choice to us. You will have to go to 2. If you are standing at 1, you have to go to 2. Can we say this? This transaction is compulsory for us. Yes or no? Yes. Now, if this transaction is compulsory for us, can we say if we directly move to 2, we need to store this somewhere? Like unless and until we store this entire tree is gone. We will never be able to find the right subtree if we just move to 2. Yes or no? Yes, no, yes, no. Yes. So we will store it in a stack. Simply. We'll store it in a stack. So let's see how this works. So the first condition. If the current node root is not equal to null, all we have to do is go to the left and like place current element in the stack. So we'll do stack dot push root dot or stack dot push root, the entire node we are pushing, and we'll do root equal to root dot left. So this basically makes sure that if you are standing at a root node, first we'll place it over here in the stack, then we'll move to the left side. Similarly for 2, we'll first place it over here, then we'll move to the left side. Making sense to all? Yes or no? So let's say the root, initially it was 1, then it became 2, then it became 4. For 4 also, we'll place it first in the stack, then we'll move to the left side of 4, that is null. Making sense? So now root becomes null. Now what to do if this becomes null? Can we say the left side does not exist? The left side does not exist. That means the last element that we selected, for that element, the left subtree is complete, done. So this element now has a priority. We can maybe always print this element. Can you say this? Yes. So let's say second part. If root reaches null, then what to do? If root was not null, we were simply pushing it to the stack and then we were moving left. Two things, simple. Just push in the stack, move left. This way we make sure that we are considering left subtree first and current element is stored somewhere that we can reuse. Now when the left part is complete, we say that whatever we insert in the last part, like last element in the stack, that should be given the priority and then we can go right. Yes? Yes, no? So can we say we can just print the top element of the stack? That is something we can do. Then we can move right. Or let me do this like this. Let's make the root equal to top element of stack. And let's remove it. We are also removing it. So we are making the root as the top element. Or let's directly write it pop. We can directly make it also pop. So let's say it is also returning its top element is returned. Now we'll just say let's print it. And let's move right. Is this okay-ish thing to do? Like first, like consider that current element, we are back with current element in our hands. That is our priority element now. Now in that particular part, print it first, then go right. So we will update this root to 4. This is removed. Now what we'll say? Give itself priority. So the output will be first print 4. Then move to the right child of 4. Right child of 4 is again back to null. Making sense? Yes, no, yes, we'll take care of those, although don't worry, we'll take care of the stacks cases. Let's continue. Now 4 is printed, we are done with 4, we don't have to worry. Right now we are standing at a null node back. Can we say the null node again? Same thing is applicable. The top of the stack is the element we should consider. Basically the left part is complete. So the current element should come into picture. Let's print the current element. Then let's move right side of the current element. That is 5. So far so good, everyone? Like what to do when the root is not null and what to do when the root is null. If it is not null, go left. Simple. And store it. If it is null, then pick out the top from the stack. That is the current element. Print it out and go right. Let's continue with this diagram. So when we are at 5, what will happen? It is not null. So we'll push it in the stack. So we'll now push 5 in the stack. Also 2 was popped out. So we'll now push 5 in the stack. Right? Now what we'll have? We have pushed 5 in the stack. Then we have to go left. So 5 dot left is 7. Okay, so we'll have reached 7. Now again it is not null. We'll push 7 in the stack. We'll go left. Left is null. Now we reach null node. 7's left is null. We reach a null node. So what you do? Currently make the current element, the top element as the current element, 7. Print it out. Then move to the right side. So right side is null again. Back to null. It is null. We have removed it from the stack. Now again, right side of 7 is also null. Let's pick out the top from the stack, 5, because we will say left side of 5 is complete. So we just popped out, sorry, this is updated to 5. We printed 5 and then we'll move to the right child of 5. Right child of 5 is also null. Right child of 5 is also null right now, right? We are currently over here, right child of 5. So basically these things are removed from the stack. Now what to do? Can we say now again the top element of the stack, one thing we should consider? This basically means left subtree entirely is complete. Yes. And in general, if you look, 4, 2, 7, 5 are only the elements of the left subtree. So this is left subtree that we successfully completed. Yes. Now what to do, guys? What is the next part? Current node, the root node itself. So we'll pick it out 1 from the stack. We will print 1 and we'll move to the right child of 1. That is 3. Right? This is now removed from the stack. Now it is not null. We will push 3 in the stack and we'll move to the left child of 3. That is null. So left child of 3 is null. We'll see that. The left child is not null. So now again we will pick out the top element of the stack, that is 3. We'll print 3 out. We'll remove it and we'll move to the right child of 3, that is 6. Correct? Now again 6 is not null. Let's push 6. Move to the left child of 6, that is null. Now because it is null, remove the top element from the stack, 6. Now print 6, move to the right child of 6. Right child of 6 is also null. So at this point of time, if you will notice, the stack is also empty and the current node is pointing to null. Can we say because current node is pointing to null, we don't have anywhere to go, so we should stop? Yes, no? We can stop. So what is the stopping condition? Guys, what is the stopping condition? Stopping condition is root is equals to null and at the same time stack is empty. Because if stack is not empty, then we can place root to the top of the stack. Yes or no? If the stack is not empty, we can always find an element from the top of the stack and we are good. Yes. So is this clear how we do iterative in-order traversal? So if I ask what is the time complexity of this particular algorithm? What is the time complexity, guys? Time complexity basically how many elements are we looking at? How many steps are we taking to solve the question? Correct. Order of n. Because every node, if n is the number of nodes, we are only going to every node once. What is the space complexity that we are using? We are using a stack space. What is space complexity that we are using? Correct. In the worst case, it can also become order of n. In the worst case, we can also store all the elements in the stack. But if we look at in terms of height of the tree, can we say the space complexity is not order of n but order of height? Like at max, we will only store one particular path in the subtree. Can we say this? At one point of time, we will only pick or put only one particular path in the like the stack. We will not have all the elements in the stack at one point of time. Yes. So the space complexity can be written as order of h. That is order of height. Also, if the tree is balanced, then the height becomes equal to what? For a balanced tree? Yes, log n. So in case if you have studied about a balanced tree, the height is log n in that case. Like in case of a binary search, in case of a merge sort, the same way. But for now, just consider that worst case time complexity order of n. And if we can represent in terms of height, it is order of h. Is this clear to all? Iterative in-order traversal. H is the height. Alright. Shall we do some insight on scalar? Like what is scalar? Like I guess you guys are enjoying studying this all. We teach like this all of the time in the scalar. Like we have a lot of classes. So I'm pretty sure all of you might have some questions on scalar. So let me just share my screen for a while and give some insights there. So Like you might have studied today, we are studying binary search trees. But before this, we also have to gain some knowledge on linked list, arrays, and so on. Like some of you who are comfortable with arrays and linked list, they are finding the today's class easy. But some of you who are not comfortable with linked list, they have to spend more time in thinking and understanding stuff. Yes? So the structure of curriculum is very, very important when we learn something new. Do we all agree? Like structure of a curriculum is very important when we learn something new, anything new. Like in our school also, we first study from basics, then step by step we increase the difficulty. So structure is very important, and that is what we mainly focus on in our scalar. So we start from DSA problem solving, then we go for computer science fundamental, that is operating system, computer networks, DBMS. Then you move to low level design, which is very important for interviews as well as the job performance. So when you start actually as a software engineer, you should know some low level design concepts. Then we move to the high level design part, which is important at a senior position. So if you're applying for SG2 or higher, that is important. Or even if you start your own startup, then it is important to know how to design a system. So for that, we have a high level design. After studying all of this, we also do a project building. So where we apply everything. This is about the curriculum. And we have a four pillar structure. So we have live lectures. That is like this. We'll study every 3 times in a week, every alternate day, you can say. Then we have 1:1 mentor. So you can say you will be, as every scalar student has one particular mentor who gets like communicate with the student on one-on-one basis. And mentor is basically a person who is at a position where you want to achieve, like you want to go. So maybe let's suppose if someone dreams to be in Google, so that person can select a mentor from Google, a software engineer two or of Google or three of Google. Then we have TAs, army of TAs to resolve the doubt. So if at any point of time you are writing a code in assignments, homework, and we get stuck, then we can always connect with TA and discuss the doubts. And the fourth pillar is always peer-to-peer learning. Peer-to-peer is always, always helpful. Then why it is different from the free courses? Because number one, the structure is very systematic. Then here we have a lot of push available. So in the free courses, like maybe interviewed lead code, if you'll do, you have to be motivated on your own. So it's like you have to go to gym on your own every day to get a fit body. But if you have a trainer who is again and again pushing you, maybe giving you a phone call that, okay, today you're not at gym, where are you? Then that extra push sometimes speeds up the process and also pushes us to increase our efficiency. So that push we get when we are at Scalar. So in every lecture, the instructor will push you, the mentors will push you, and the doubt solving is immediate in Scalar compared to free platforms. So there you can post your messages. Other people may reply, may not reply. Here TS will definitely resolve the doubts. So Scalar will push you and give you all this form of support and learn to move forward. Then the past data is that we have seen salary jump of 2.58x on an average. So basically less than 3 years people experienced have got a 16.5 LPA. 3 to 7 years experience people have got a 22.5 LPA, and 8+ years experience people have got a 39.5 LPA salary jump. That is a past experience CDC bucket. And here are some people: Kritika, Mitush, Soumya. And one among these we have Manikya today with us. Manikya, hello. Are you there?
Yep. Hi, Utkarsh.
So Manikya was one of our students, and today he is here to share his journey for everyone. So in case you have any doubts, you can also ask Manikya. So Manikya, please introduce yourself.
Sure, sure,
Maybe
sure.
you, if it is great.
Yeah, I'll. Okay, so Manik, I've been like a 2019 grad. Like electronics was my majors. So I joined Scalar in 2019. I was in 2019 October batch. Yep. Currently, I'm working with Amazon as an SDE. I've overall worked for 2.5 years. Any particular questions you want to ask, please shoot.
Guys, Manikya is one of our ex-students, you can say ex-alumni, who
Yes,
is
I was
working
a
at Amazon. So if
yes,
you
I
want to
was.
ask anything, you can ask. So meanwhile, Manikya, can you share your journey? Like how you came to, like, how you
Sure.
got the interview, then how you cleared the interview, what were the difficulties?
Uh, got it. So I was an October 2019 batch, so I by the time I was ready for interviews, it was February, March. So at that time, it was like a complete shutdown of hiring. So, but later on, with the Amazon interview, how I got it is like Scalar helped me with a referral. Like some of the mentor was working there, so they arranged a referral for me.
Mhm.
So that was the first referral that I got. Second time, but at the same time, I got another offer. So I choose another offer because I already accepted that one. But second time I got was the same HR. They had my resume already in the code base or something, like in their base or something that they reached out. So that was the second time.
Hmm.
Yep. So that's my journey how I got the interview. But yeah, there are like multiple ways you can. Like usually referrals do work. Direct applications won't work. That we all know. So yeah.
And how were the interviews experience? Like, how were the easy, were the difficult?
Interview, I'll say it's easy. Like the hard work is just done before interview itself. Like learning DSN, that's the only hard work you do. Interviews are like not that difficult to crack if you know the fundamentals and stuff, and it's easy to crack interviews.
And does the scalar journey help you there?
Yeah, yeah. Okay. So just to give you an idea, like I had never coded before, and like I started with HTML, CSS. That's all I knew, and then in college I did that. I did not like CSS at all. I left it. I don't. This is not my cup of tea, and then I left it. So Scalar is something somewhere that I started learning because the first job I was in, I wanted to skill up, and I knew I had a lot to learn. So Scalar is something where I started learning uh, in a systematic way.
So you did not have computer science in your college?
No, no, no. My majors was electronics and communication.
Oh, so you basically jumped from electronics to computer science
Yes,
and
yes,
then
yes,
started as
yes, yes.
software engineer.
So I had
Nice.
a lot to learn. Not just data structure, like computer networks, DBMS, all these subjects were kind of new to me. So it took me some time to get a hand on all of that.
Nice, nice. So guys, Manik is like a live example in front of you that like your degree does not matter. Like if you are from any branch, if you want to learn computer science, that's always possible. Always,
Mm.
always possible.
Yeah, that's it's so true. Matlab, even I'm like from electronics, but that's somewhat related to computer science. But I remember we had people from every branch, mechanical, civil, and all of that other branches. So that graduate my graduation year is like 2019, guys.
So we have one more Tejasvi from CEC branch. Nice. All the best. Any
Okay,
tips you'd like to share to all like if any general tips?
okay. Any general tips? Uh, okay. With respect to course, I'll say ki if you just stick to a course, don't switch courses. That's all I say. Take a course and then stick to it till the end. I'll so like 3 months of hard work. Consider like a 3 months of hard work you have to do. At least I'm saying 3 months of hard work that covers. I guess because that's still like 3 months of DSA, right?
Yeah, three to
DSA.
four,
Yeah,
4 months usually. Yeah.
yeah. Okay. Yeah, well, the advanced section segments T's and that take like the last month, but 3 months I'll say like give it
Intermediate
all
level,
you have.
basic.
Yes,
Nice.
interview preparation. Like, that's the 3 months of your course. Give it everything, and you'll not regret doing it for sure.
That's a
So
start, by the way. 3 months is a start. After that, you
yes,
have to study computer
it's minimum
fundamentals,
time.
and then design. Design is also important. Like actually how we do in companies.
Yes, true, true. So
So nice. Any one experience you'd like to share of Scalar? Any one incident, any experience? Last question from my side,
okay,
promise.
one experience. Yeah, I had very very good experiences. I was fortunate enough to get a good TAs who helped me, resolve all my questions because I had a lot of them. Uh, to be honest, when you start, you have a lot of questions. Everyone is able to solve questions, and you have a ton of questions to ask. So ask questions. That's what I say. That's what I did, and that did help me a lot. Yeah, peer learning is something that will definitely help you a lot. Uh, and
Nice.
yeah, have fun in the way, make friends.
Yes, that is important. Peer to peer is obviously very important. We have some questions from students. Like Ravi is
Yeah.
asking, what is your work in Amazon? Like, what do you currently work on? Kranti is also asking same.
Okay, currently I'm working with the Amazon App Store team, their SDK team.
Okay, okay.
Uh,
So she's asking, is web design a good career? So any point of view on that?
if web design a good career, depends for person to person. If you like it, do it. If you don't like it, don't do it. If you like data science, if you like any other stream, do it. if you push yourself, you're not gonna do anything good in any of the streams. Not just web development. Do it. See if you like it. If you like it, continue. If you don't, like just leave it.
That is the best example. That like best answer I can say. Whatever you like, then only you should do it. Otherwise, it's not good.
Yeah, like you cannot force yourself to do it. Yeah, I'll say yeah, web development is a very good. You will make money. Like, it does not work like that. You should enjoy doing it. Otherwise, you will not be able to do it for long.
Yes. They are saying, Joy is asking what type of questions were they asked during the interviews. So, any
Uh,
interview question do you remember?
okay. I remember like one of the question was regarding heap. One of the question, if you ask me like exact questions, I do not remember to be honest.
This topic
But
is
yeah, topics I'm telling you. One was from heap, one was from a tree. Uh, but nothing too fancy or something that you will not you know uh, not learn on the journey. It's like basic things only. One was free, one was heap. That's all I remember. I do not remember the third one, or maybe more questions were there. But yeah, basically these only. So it's not very much difficult. Just focus on the basics and fundamentals. Keep them strong. Don't cram questions. You'll be good to go.
so basically maybe today we are solving one of the Amazon questions interview.
Oh, nice, nice.
Yes.
And guys, there's a question like CP necessary to get into Amazon. Like CP is not necessary to get into most of the companies,
Yes.
except a few of them. But most of the companies you do not need CP to get into any of the company.
Yes. Guys, CP is a not a prerequisite. It's a good to have thing, but it's
Yes,
not a compulsion to have.
yes,
So if
yes.
you know CP, that is good. But if you don't know, that's okay. That's not a very
Yeah.
problematic
Don't
stuff.
don't do CP because you want to get into a company. Uh, do smart work. If you like like competitive programming, do it then. Otherwise, focus on interview prep if you want to just crack the interviews.
Yes. And the CP is very awesome if you have time.
Yeah, yeah,
If
yeah. If you like it, it's addictive, but
hmm,
it's really addictive.
yes. Okay, one last question I guess we can take. What are your point of view with respect to startups and Amazon? Like if you compare Amazon with a startup, like any point of
Uh,
view there?
yeah, I've worked with both. My entire past journey before Amazon was all startups. I really enjoyed startups, but uh, I'll tell you, I have two experiences. Like it can be very good, it can be very bad, depending upon which company you are working with. If you have people who are great, you'll have a very good experience. If the company does not have a very good environment, it's gonna mess your life up and down. uh, so startups, you learn a lot. It's a very good experience, but look at the company you're going, that's all.
Hmm.
And
Well said.
now I'm working at MNC. It's I'll say it again depends upon the team you're working in.
Hmm.
If your team
Yes.
is good, you're gonna enjoy your work. If your team is not good, it's not gonna matter which company you are. It's a team.
Yes. So basically every sub team we can say is like a startup in a company.
Yes, yes.
Nice, nice.
And this with competitive programming or projects, it's again a personal thing. Some people excel in development, some people excel in like competitive programming. It's up to you. Whatever you like, do it. Don't don't do it just because for the sake of cracking interviews. You need basic DSA. That's all you need.
Yeah, it's totally optional to select computer programming or projects. It's not compulsion to do both at the same time.
Yeah.
Because
Try.
anyway, when you join the company, you will know okay what the company is working on, and you will understand what they have to do and what you have to learn there, and then you will start working on it.
True, true, true. So just simple, yeah. Try whatever you like, continue that, leave the other one.
Yes. I hope we have answered a lot of questions.
And there's a tech stacks, yeah. Tech stack changes with project, changes with company. Don't worry about tech stack. You will learn it on the way. The certification matters, not really.
Not really. Like honestly, people have not even seen my resume a lot of times when I apply for interviews.
Yeah, they don't even like. You can mention any certificate. They won't even ask you until unless it's a very highly certified thing. And even then, they don't ask it if you have it or not.
Thanks, Manikya. Thanks for joining
Okay.
in.
And yeah,
Guys,
thank
here
you,
was
Utkarsh. Thank you
Manikya.
for having me.
Thank you very
Yeah.
much. The next part, that is the binary search trees. Okay, how many of you have heard of this term binary search trees? Like, how many of you have heard what is the binary search tree? Like, just the term binary search trees. Okay, we have some people who have heard of this term, some people have not heard of this term. That is totally fine. A binary search tree is a specific kind of binary tree which has a structured way of storing a data, right? In a binary tree, the structure and everything we discussed in the first part today. In the first part, we understood what was a binary tree looking like. What are the terms, like what is the left subtree, what is the right subtree, what is the leaf, what is the root, and all the terms. But we did not discuss how to store a data. We discussed that we can store data in any order that we want. In the second part, that is the traversal part today, we discuss how do we travel the data. So how do we find any particular data? How do we use the data in whichever order we want? Now, third part is inside the tree. How can we organize the data so that the searching becomes efficient for us? As the name suggests, binary search trees. The main idea of binary search trees is basically to optimize on searching. Is that making sense? So it's like a binary tree which is optimized for searching. So how do we optimize our data, or how do we organize our data in a binary tree so that searching any specific thing becomes easy for us? That is the overall idea of binary search trees. So binary search trees says that we can organize our data such that if we are standing at any node, so for example, if we are standing at any node, so let's say root node, then for everything in the left subtree and everything in the right subtree, left subtree should have all the small values, right subtree should have all the bigger values compared to the node which we are currently standing at. So for the current root node, if we have certain value at a root node, everything here should be less than root and everything here should be greater than root. Now the question comes, what about the equality? What if the root has maybe a data of 5 and we want to store 5 one more, like 2 5s if we want? What should the equality go? So equality go at any location, but throughout the tree, it should be at only one side. So you cannot say that if there is 1 5 we are putting in the left subtree, another 5 we are putting in the right subtree. Both the equal cases should be on one side. So for our purpose, we can say that, okay, let's pick the equality on the left side. If you want, we can also do the equality on the right side. Totally fine, no problem. Making sense to all? So equality is something that's totally our call. Wherever you want to design, you can maybe put it on the left side, put it on the right side, totally our call, no problem at all. So if we write it another word, let me write it. For all nodes, node dot data is left subtree, or yes, node dot data is greater than equal to left subtree data, and node dot data is smaller than right subtree data. Is that making sense to all? Yes, no? Any side in general. If you want left side, if you want right side, equality can go anywhere. No restriction on equality. All right. So let me uh, draw a tree. Let's draw a tree. We have 10 as the current node. Left side, let's pick 5. Right side, let's pick 20. Let's pick 2. Then let's pick 7. Then let's pick 15. Let's pick 22. 21. Let's pick 6. No, let's not do the 6. Let's pick 9. And let's pick 8. Guys, is this particular tree a binary search tree? No. The majority of you are correct. The answer is no. It is not a binary search tree. Why? Because if you look, this particular 8 is not at the correct position. Basically, if you look at 5, the left side of 5 is having a smaller value. Sorry, 15. Left side of 15 is having a smaller value, which is good. We don't have a problem with that. If we look 20, left side of 50 is, or left side of 20 is smaller, right side of 20 is bigger, everything is good. If we look at 10, then the right side of 10 is not having all the values bigger than 10. Is it making sense? That when we look at 10, the right's entire thing should be bigger, but this 8 is not bigger. Hence, we can say this is not a binary search tree. Is this clear to all? Why this is not a binary search tree? Because of 8. So any node, for every node, all the left part should be smaller or equal, all the right part should be bigger. Making sense to all? Even if there is one node that is violating the entire thing, any one data, that violates the entire tree purpose. It's not a binary search tree anymore. So if I remove this, is this now a binary search tree? Yes, no, yes. Now it's a binary search tree. Because for every node we can see left side are smaller, right side are bigger, and everything is good. Right? Now, let's suppose if as we say that the main idea of binary search tree is to optimize search operation. Correct? Main idea of binary search tree is to optimize search operation. So let's see how the searching works. So let's say if someone asks us to maybe search, let's say 6. We have to see if the 6 is present or not in the tree. If we have to search for 6. We always start from the root node as usual. Any ideas how we will search for 6? Like if we travel it like the above case, that is a version 2, that is pre-order, in order, post-order manner, we have to travel the entire tree and we can say, okay, we will be able to find our 6 if it is present. If it is not present, we can say it is not present. But that will take time complexity order of n. We have to see all n elements. Then we can say that, okay, yes, 6 is present or not. Can we use the property of binary search tree and make searching easy for us? Like, is it making sense what the question is saying? The question is saying that try to use the property of binary search tree so that we don't have to look all the elements and maybe only few elements and reach 6 if it is present. So how do we do it? So we start from 10. Guys, since 10 is greater than 6, can we say all the right subtree elements will also be greater than 6? Like all the right subtree elements will also be greater than 6 because the current node is greater than 6. So is there any use going in the right side? No, we can just keep it. So we'll come to the left subtree. Making sense? Now in the left subtree, it is smaller than 6. So can we say there is no use going in the left side because everything will be again smaller than 6? So let's move to the right side. Now this is again greater than 6. So again we can ignore this and we are here. And we can say, okay, yes, we are successfully able to reach this particular node, 6. So 6 is present. So we basically traveled what? We basically traveled from 10 to 5 to 7 and we reached 6. So we don't have to travel the entire tree. We just traveled 4 nodes and we are able to reach our destination. Is this searching making sense to all? How searching is working? Yes or no? So is it somewhere related to binary search? Like, do we remember binary search approach? In the binary search, in an array, if you are standing at a node, if it is sorted, you can just discard the left or the right side depending on what is the value at the node. Similarly, in this case, you can discard left subtree or right subtree depending on whether you are currently standing at. Right? So let's do one more example. Guys, let's say if someone asks us to try and search maybe 18. Okay, this is the question. Someone wants to know, is 18 present or not? How we will search 18, guys? Where is the 18? Equality can be anywhere. Okay. Nice. So if we have to search 18, we'll say 10 is smaller than 18. So if 18 is present, it will be present on the right subtree. Correct? We can discard the left side. Then 20 is greater than 18. So we'll say if 18 is present, it will be present on the left side. So we discard the right side. Now 15 is again smaller than 18. So we say if 18 is present, it is present on the left side, right side. And we can discard the left side. Now right side of 15 is actually null. There is nothing there. So can we say it is not present? So even if we travel, this make a traversal of 10 to 20 to 15, but it is now pointing to null. So we can say 18 is not part of the binary search trees. So is it making sense how searching is good if we have a binary search tree in front of us? So if someone asks us, what is the time complexity to search? What is going to be the answer, guys? Correct. Order of height. Very good. At max, one chain we have to travel to check if a element is present or not. Time complexity is, Rahul, is basically how many elements are you traversing? How many elements are you looking at any point of time? Like total number of steps taken to find the answer. So it is order of height. Very good. Only one chain we are traveling. We are not traveling more than that. Nice. So is the searching clear to all? Like how searching is working? Nice. Let me ask one more question, shall we? The question is the smallest value in binary search tree always a leaf node? Yes or no? Do you feel is the smallest element in binary search tree will always be a leaf node? All right. Unfortunately, majority people are incorrect. The answer is no, guys. It is not the smallest element always a leaf node. Why? Because currently you can say, okay, yes, it is a leaf node. We have a smallest element always a leaf, right now a leaf node. But what if, let's say, as this was 2 over here, I have a right child of 2 that is 3. Now, what is the smallest element? Can we say the smallest element is still 2? This is our smallest element. Yes. Can we say the smallest element is still 2? The smallest element in the entire tree is still 2. Yes. But it is not a leaf node because it has a right child. Definition of leaf node is that both left and right child should be null. So like we did above. Definition was for a leaf node, left and right child both are null. Here only the left child is null, right child is not null, so it is not a leaf node. Is it clear to all? Now if I ask, how do we search smallest element or minimum value? How do we search minimum in this particular binary search tree? Correct. We basically travel left till we reach the last node from where we cannot go left. Make sense? How do we search minimum? Go left till it is not null. So for example, what we'll do, we'll start from a root node. So while root dot left is not equal to null. So there is something present at the left side. We'll do root is equals to root dot left. That's it. So if there is anything present at the left side, just make root equal to root dot left, and we will be able to reach return root. This will now be our minimum element. Is this clear to all? The tree will follow the property everything on the left is smaller, everything on the right is bigger, Shant. So it will be like this. Alright. Similarly, can we say the same thing is applicable if we have to search maximum? Yes. So go to rightmost node. That's it. So this is basically our maximum or largest. Is this clear, guys, that binary search trees are not only helping us searching a specific value, they are also helping us searching the smallest and the largest entry as well. Yes, clear to all? Now if I ask, what is the space complexity required to do any searching operation? What is the answer, guys? Space complexity. Correct. Constant. Well, the answer is constant because we are not at all storing anything, not even recursion, nothing. We just have to basically travel left, right, and we will reach our answer. Yes. For example, if when we are searching a minimum element, yes. So when we are searching the minimum element, what happens? We are just going left, 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 and we are not storing anything anywhere. Similarly, if we have to write the code for searching any element, how we'll write the code there? So what we'll do? We'll see, okay, let's suppose we have to search any particular value x. So search x. What we'll do? While root is not equal to null. Okay. We will say if the current root data is equals to x, we can return the root node. That this is the node that is storing our data. Else if root.data is less than x, then what to do, guys? If the data is less than x, so currently you are setting it a smaller value. Root is smaller, x is bigger. Guys, if root is smaller, so if suppose we are searching for 20, yes, why are we saying left? Right, we have to go right. So root is equals to root dot right, because currently we want to find a bigger thing, bigger value. Else we will say go left, root equals to root dot left. Making sense to all? Is this clear how things are working over here? Yes, no, yes, no. If we look at this particular code, and in the end also we can return null node, indicating that it is not present, so not present. Is this clear? If we have to indicate that data is not present, we can just simply say it is not present. What is the time complexity? Like how many steps are we taking to reach the answer? How many nodes are we looking at to reach the answer? Height, very good. Because we are traveling one particular change from the root node to the current node, very good. What is the space complexity? Like how, is there anything that we are actually storing somewhere? No, so it's constant. We not do not use any stack, anything, stack, queue, anything. We are just not storing anything extra. So space complexity is constant. Is it clear to all how things are working? Yes, 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 yes. So ready for one question that was asked to me in my Microsoft interview. Space complexity is calculated, Shubham, based on how much extra space are we using, like how are we storing. So for example, in this case, we were using the stack space. So we use a data structure to store something. So it was order of h. Here we are not storing anything extra. So space complexity is constant. So if you have to find all the possibilities and you know that the element, so guys, we have a good question. What if there are multiple fives and we have to search all the fives? In that case, you can say that whenever you find, you don't return it. What you will do is you will go left, because you know current element is equal, but all the equal elements are also on the left side. So the question, if the question is find all the occurrences of element x, view will do the same thing, like we will do the same thing. If it is small, go left, bigger, go right, same thing. But if it is equal, then also we'll go left, because we'll say that if there is more element of value x, they are always on the left side. Is this clear to all? How to handle equality? Nice. So let's do one question, one interview questions. It was asked to me in my first face-to-face round. The question is whatever I just now did over here. So we have to check whether a given tree is a binary search tree. That's it. Check if the given binary tree is a binary search tree. So all you have to do is check whether the given tree is a binary search tree or not. Now, please take 2-3 minutes and try to write a code of this in a pen paper if you have, or maybe in the laptop or computer, another tab you can open, and you can use any online editor, IDEO editor or any editor, and then code there. So take 2 minutes, have a thought, how do we find or check whether the given tree is a binary search tree or not? For example, if I write a tree like this, 10, 5, 20, 2, 7, 6, 12, 22. Guys, is this a binary search tree? No. So in the code, how we will check it? Now, guys, please pay attention. This is a very, very important thing. And this will make you realize why it is actually an interview question. Okay. Now, how many of you feel this is a very easy question? Like when we look at it in the first side, we know, okay, yes, this is a very easy question. All we are just have to check the left side, right side, small or bigger, everything is good. So have you heard of that joke? Like, दूर से देखा तो ये था, then पास से जाके देखा तो something else came up. I'll show you that thing today. So, दूर से देखने पर it is a easy thing. Like when you're looking at it from far side, it's a easy stuff. Let's see closely. Now, many times, many people answer this like, let's check the in-order traversal of this and it should be sorted. So, in-order traversal of binary search tree is sorted. How many of us believe this? That in-order traversal of binary search tree will be sorted? This is a very common answer for this question, which is in some way a correct answer. Because if you look at an in-order traversal, what is it? It is saying left node, right, left node, right, which will always be a sorted order for a binary search tree. Any binary search tree, if you will pick it up, it will be a sorted order. Let's take the above tree. Guys, what is the in-order traversal for this tree? Like if I have to write in-order traversal, what is the in-order traversal for this particular tree? We have first 2, then 3. So we start from the 10, then we go to 5, then we go to 2. Left is not there, we'll print 2. Then we'll go to the right side of 2. We'll go to 3, we'll print 3. Then left side is complete, so we'll print 5. Then we'll go to the right side of 5. 7, we'll go to the left side of 7, 6. Then 7, then 9. Left subtree is complete. We'll print 10. Then 10 is complete. We'll go to the right side, which is 20. Then we'll go to the left side of 20, which is 15. Then 20 back, current node. Then the right subtree of 20, which is 22. Then we'll go to the left side, 21, and then we'll go to 22. Little a long tree. Is this in-order traversal clear to all? Like left, current, right. We spent some time on in-order traversal. Now, do we all agree that for all binary search trees, in-order traversal will be sorted? Draw any binary search tree. In-order traversal will always be sorted. That is a very correct statement. This is a correct statement, guys. Because we are always going left first, so all the smaller values are covered, then node, all the current values are covered, and then the right side. So it will always be sorted. But is the other way around true? That is a question. Now, if you look at this tree, maybe if we write the in-order traversal of this tree, what is the in-order traversal of this particular tree? Correct. In-order traversal of this particular tree is 2, 5, 6, 7, 12, 10, 20, 22. Right? Now, this is not sorted because if you look, 12 is greater than 10 and it is before 10. It is not sorted. Since it is not sorted, we can guaranteedly say it's not a binary search tree. Can we say this? Because for every binary search tree, it has to be sorted. And if it is not sorted, by guarantee, we can say it is not a binary search tree. Right? But what if we make some changes? Let's say, this was 10, okay, and this is 10. Now, is this a binary search tree? No. Very good. Reason? Because equality is distributed on both the sides. Correct? Definition of binary search tree says equality should be only on one side. That's totally our call. We can maybe have it on left side or right side, but not both. If I do the inorder traversal now, what is the inorder traversal now? Correct. Bharat, very good. 2, 5, 7, sorry, 6, 7, 10, 10, 10, 20, 22, which is sorted, but this tree is not a binary search tree. So is it clear that if the inward traversal is sorted, it does not guarantee that the tree is binary search tree. If the tree is binary search tree, inward traversal is sorted, that is guarantee. But the vice versa is not true. Now, how is it looking when we look at closely? Like, how it's looking when you are close to that? Like from far away, this statement is very obvious. But closely, this statement is making trouble for us. That's why it's a interview question. Because this is a common mistake people do during the interview. So if something like this comes to you, please pay attention and please don't make this mistake, because now we have seen this mistake, right? In-order traversal is sorted for all binary search trees. But if a tree is not a binary search tree, it is also possible that in-order traversal is sorted. Like this example. This is not a binary search tree, not a binary search tree, but in-order traversal is sorted. Making sense? Very important trick that we miss out many times. So how do we solve these kind of cases? We solve this kind of cases with a simplified version of the definition of binary search tree. What is simplified version? Guys, this is a definition of binary search tree. Let me use this out. So this, using the cool feature, like this. For all the nodes, yes, climax here. We want that the data should be greater than equal to left subtree data and less than right subtree data. Can we, based on this, also say that node dot data should be greater than equal to? Now we want it to be greater than equal to for all the left subtree data. So can we say it should be greater than max in left subtree and node dot data is less than minimum in right subtree? Is this making sense? Because you want to compare it with all the values, why not just compare with min and max? If we compare with min and max, everything is great, now. So far making sense? Yes. So how do we calculate min and max of a binary tree? Let's look at it. Shall we? Okay, let me repeat this once again. Is this clear? Like how the definition of binary search tree? That for all the nodes, we have to maybe look at the left subtree if it is smaller and equal, and the right subtree should be bigger. Then we can say, okay, current tree, the binary search tree. Now, if you are saying all the elements in the left side is smaller or equal, then the maximum value in the left side should be smaller and equal. Because if the maximum is smaller or equal, then everything will be smaller or equal. Similarly, on the right side, if the minimum is greater, then everything is greater. Yes? Can we get a quick yes if this part is clear? This important part, this is a very important part. If this is clear, then the question is 90% solved. Now, one question comes to mind. If we have to find the minimum and maximum of the left subtree, of the right subtree, then what kind of traversal should be used? We have seen in order, post order, pre-order, right? So what do you think? Which traversal will help us get the min and max of the subtree? Try to see, do we need to give priority to the left side, right side, then the current node? Do we need to give the priority to the left side, then current node, then the right side? Or do we need to give the priority to the current node, then left and right? So what should be the priority order? That will define our answer, guys. Guys, the correct answer is post-order traversal. Now, why we say post-order traversal is best? Why not pre-order? Why not in order? So for that, let's observe it like this. When we decide a traversal, we decide on priorities. Left is important, current is important, right is important. That's the main idea of deciding which traversal do we need, right? Yes, no? Come on, guys. Yes, no? That is an important parameter to decide, like which is to be given more priority. So tell me one thing. If you want to find for this particular node the maximum from or minimum like of this entire subtree, can we say we will need the maximum and minimum in the left subtree and the right subtree? Then only we can find maximum and minimum of the current node. Yes or no? First, we will need the maximum and minimum from the left subtree, then the right subtree. Then we can decide, okay, current element is like how to calculate the max or minimum for the current element. Is it clear to all? Let me show this via code also. Shall I? I'll show the max and min, then we'll discuss how we'll check the binary search tree. So let me write the code for this. So let's say we are taking a pair. So we have a class pair, which is basically storing nothing but min and max for us. So we'll have, let's say, int min comma max. Okay, we have a player which is storing min and max for us. That's it. All right. So pair travel route. Guys, what is the first statement that we always write in any code of tree? Correct. Root is null. If the tree is empty, if we are standing at a null node, what should be returned? So let's say we are returning maybe max comma min or min comma max. So let's say max comma min. Max comma min is something we have to return. All right. So can we say the maximum should be the minimum value, like smallest possible value, like integer dot min, int dot min. And for minimum, we can give the maximum value. That is int underscore max. Just to make sure that if we have to calculate maximum, the maximum will be computed whichever the next value is there, because current is very small. So whichever the next is there, we'll just take it out. Right? So then let's calculate for left subtree. Travel. Root dot left. For the right subtree, travel root dot right. Now we have computed the left and the right subtrees min and max, and let's suppose we have to find the min and max for the current node. Okay. Now, what will be the maximum value of the current node? Can we say it will be maximum of current value or the right subtree? So maximum of current node or whatever we get from the right subtree. And minimum will be minimum of smaller of current node and left minimum. Let me explain this now. Yes, so how we are working, how we are doing things. We are saying if we are at a node, which is a null node, then we are returning minus infinity to infinity. So for example, it is like minus infinity to infinity. Let me write it like this: minus infinity to infinity. Okay. Infinity can be any number. You can define a infinity maybe as 2e9, 2 into h bar 9. You can define it anything. 2 into h bar 9, something like this. You can define any biggest value. Okay. Now, what we are trying to say is, as soon as this null empty, like as soon as we reach any node, which is a non-null node, we want that particular node's data to be min and max. So this will take care of those cases. So if we are returning from a null node as a left or the right side, the current data will take the place. Otherwise, if it is a binary search tree which is given to us, like it should be a binary search tree, then the right side will have a bigger value and the left side will have a smaller value. So we'll just take the right side or the left side. So let's do a dry run and see this. Before this, let's also write the conditions that are important to check whether the current tree is a binary search tree or not a binary search tree. Right? So let's say if initially we had a variable is binary search tree, which is saying it's a binary search tree true. Can we just check in between the traversals? If at any point of time it fails, the condition fails, this condition fails, then we will say it's not a binary search tree, not a valid binary search tree. So if, let's say, root.data is less than left dot maximum value. So left subtree's maximum value is higher, or root.data is greater than equal to right subtree's minimum value, we can say is binary search tree is updated to false. Now, if at any point of time, even once it is updated to false, it will never be back to true. If at any point of time it updates to false, it will never be back to true. So anytime it violates, things are gone. Now let's do a dry run on this, the entire code, shall we? Now directly looking at a code may look tricky a little bit. Shall we do a dry run? Yes, to all. So this is a tree. Okay. Let me maybe pick this up, copy, paste. Oh, it was not copied. Copy, paste. All right, this is our root. Let me update this back to 12. And let's see how things are working. Okay. So we are currently standing at the root node. We know it is not a left subtree. We'll just go to the left or the right side. Yes, no. Yes. We'll go to the left side first. Okay, before that, guys, do we all agree that before going to the left or the right subtree, we cannot define max and min for the current node? Do we all agree before going to the left or the right subtree, we cannot find the max and min for the current node? So do we all agree post order traversal is important here? Is that clear? Like the quiz, last quiz that we did, that post order traversal is important because priority should be given to the left or right side. Then the current node should be given the priority. Yes. So let's see. Now we are at currently this particular node 5. Again, it is not null, so we'll go to the left side. Again, it is not null, we'll go to the left side. It is returning null. Now this null will return minus infinity and infinity. So it will return minus infinite and infinite as a max comma min value. Similarly, the right subtree is also null. It will also return the same thing. Now in this case, when we will return from 2, what should be returned? What is the max and min for this particular subtree 2? Can we say 2 comma 2 should be returned ideally? Right? 2 comma 2 should be returned. So this particular part is taking care of it. This particular part. Because if right side maximum is also smaller, we will take root data. Similarly, left side like minimum is big, like bigger, we'll take this data. Is this clear? That if right and left both are null, the values that we are getting, minus infinity and infinity, will be not considered and the current data of root will be considered. Yes, no? Is that clear to all? When we are returning minus infinity, infinity, so what is right max? So root dot data at this point of time is equals to 2. R dot max at this point of time is equals to what, guys? Minus infinite. L dot min at this point of time is what equal to? Infinite. So maximum between root data and R dot max is root data. Minimum between root data and L dot min is root data. So root data is considered as an important thing. Clear? How leaf node is taken care of, is that clear to all? Right? So now we'll go to the right subtree, that is 7. Then from the 6, what will the maximum and minimum? 6 comma 6. Same way from 12, maximum and minimum 12 comma 12. Yes? So when we have to calculate for 7, what to do now? Now based on again the same thing. When we are calculating for 7, the root dot data is now 7. R max minus infinity, because we are returning for null node this minus infinity and infinity. So for null node, R like maximum value is minus infinity, smallest value, and for null node bigger value is the like max is minus infinity, min is like plus infinity, you can say. Makes that? All right, coming back to this. Now for 7, the root data is 7. R dot max is equals to 6, I would say. And L dot min is equals to, sorry, R dot max is equals to 12. L dot min is equals to 6. Yes. So in this case, what we'll do? We will select R dot max and we'll select L dot min. Correct? So it will be maximum is 12, minimum is 6. Yes. Max comma min we are taking. First max, then min. Now this will be returned. Now we have to calculate for 5. For 5, root data is 5. Left subtrees minimum is 2. Right subtrees maximum is 12. Correct? So what to do? Maximum is 12, minimum is 2. Correct? Now we'll go to the right side tree, 2, 20. Now left side of 20 is null. It will get minus infinity and infinity. Right subtree is however 22 comma 22. Now when we are calculating for 20, root data is 20. What is R dot max for 20, guys? 22. Very good. What is L dot minimum for 20? Minimum value of the left subtree? Correct. Minimum is infinite. Because it is a null node, for null node we are returning minus infinite and infinite. Therefore, the minimum value will be plus infinite. Now, what is selected? The max is 22 and minimum selected will be root data, that is 20. Is that clear to all? Now for the last part, 10. Current node is 10. What is the right maximum? Right maximum is 22. Left minimum? Left minimum is 2. Left minimum. Yes, left minimum is 2. So for this, the maximum will be 22 and minimum will be 2. So is it clear how for every node we successfully found the max and min in the subtree? Yes. And if at any point of time this statement becomes true, that the left side is having a bigger value or the right side is having a smaller value, we can say binary search tree condition becomes false. And even for one node it becomes false. It will remain false. It will not update. Make sense? So basically when we were at maybe 10, when we were actually standing at 10, this is the left side, this is the right side. Root dot data is equals to 10. L dot maximum, what is L dot maximum, guys? Is equals to 12. What is R dot minimum? Is equals to 20. Can we say this condition, this particular condition is failing? This particular condition is true. That is 10 is less than 12. Because it is true, it is becoming false, and we are saying it's not a binary search tree anymore. Is this clear? How we came to this? Nice. Let's discuss the time and space complexity of this. Thanks for the feedback, guys. Thank you very much. So, if we have time complexity, if we have to look at time complexity, what is the time complexity to check if the current node is if the current tree is a binary search tree or not? Order of n. Very good. Because we are just looking at every element once. The important question is, what about the space complexity? Are we using extra space over here? Are we using the extra space of the entire tree size, or are we using the extra space of height size? So is it order of n or order of h? What is it? What do you guys feel? Are we using the space equal to the entire tree, or are we using space equal to height? Constant? No. No, it's not constant. Correct. Majority of are correct. The answer is order of height. Guys, we are not storing all the minimas and maximas in any data structure. So we are not storing it, all the minimas and maximas. We are just calling the function which is returning the minimas and maximas. Now this function call, recursive function call, will go in one particular chain to as deep as possible. So it will cover the entire height, cover the entire depth from one particular node to the leaf. That is same as the space complexity in any traversal if you'll do. So is this clear? Why space complexity is order of height? One traversal completely stored in stack, and the time complexity is order of n. Alright, this was it from our side today. Today we discussed three important part of hierarchical data structures. We discussed binary trees, how binary trees work, what is a binary tree. We discussed the name and nomenclatures. We discussed depth, height. Second part, we discussed traversal in binary trees, the in-order, pre-order, post-order traversal, recursion and iterative, both the traversals. Then we discussed binary search trees. In binary search tree, we discussed what is the binary search tree, why it is called binary search tree. Also, we did one Microsoft question, Microsoft question, which was fun. Let's do a puzzle. Let's do a puzzle. Let's do one interesting puzzle. Guys, so if you have a tree data structure which is like this, okay, maybe this complete tree, perfect tree, binary tree. For a binary tree is a binary tree in which all levels are completely filled. So all levels are filled completely. So basically, this is our level number 0, this is our level number 1, this is our level number 2. So all the levels are completely filled. If there is more nodes, we'll have like 8 elements. It will never be like there is an incomplete level. Okay, so we have 8 more elements. This is our level number 3. Is a perfect binary tree term clear to all? Perfect binary tree term. Like all the levels are completely filled. It is perfectly balanced. What is the height of a perfect binary tree with n nodes? So if we have n nodes, what will be the height of a perfect binary tree? Nice, nice, nice. Guys, let's see. Let's see how we have the answer. We have one element and the first level. We have two elements in the second level. We have three elements in the third level. We have four elements in the fourth level, and so on continuing. Yes. So basically we have 1 plus 2 plus 2 square plus 2 cube plus so on. Sorry, not 3 or 4. This is 4 and 8. Yes. So this is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power h. Elements. Yes or no? Can we, this is a total number of elements. This is equal to n. Total number of elements in the tree. Yes. Now if we do this, what is the sum of GP? This is GP. First term, common ratio, total number of elements plus 1, minus 1 upon common ratio minus 1. Geometric progression. This turns out to be 2 to the power h plus 1 minus 1, which is equals to our n, which implies 2 to the power h plus 1 is equals to n plus 1, which implies h plus 1 is equals to log base 2 n plus 1, which implies h is equals to log base 2 n plus 1 minus 1. Is this puzzle clear to all? Like small stuff. So we started from calculating total number of elements. It is 2 to the power 0, 1, then 2, then 4, then 8, then 16, then 24, and so on till 2 to the power height. It will be there. Adding this up will be total number of elements, which is equals to n. Now this is a geometric progression. So geometric progressions is basically summation is a common ratio raised by total number of terms minus 1 upon common ratio minus 1. So using that formula we get this. Rearranging the terms we get this. Taking log on both sides we get this. And finally answer we get this. Is it clear to all? So I hope you guys enjoyed today's class. See you in the next class, guys. Bye bye. Take care.